Okay, everyone, thanks for waiting. Again, this is Betsy Scott with IBACOS. Thanks for joining us today. For those of you who registered a week or two or three ago, originally Rich Baker was going to be joining us today. He had a family emergency, sends his regrets. But we have the very capable Anthony Grazzolia on our team. Anthony's kind of laughing at me, in his place today. This is just a snapshot of the current members in the Alliance. We have several builders on the phone today. We'll also have a lot of our sponsors joining us, and would like to take a moment to thank our sponsors for making today's webinar possible. Certainly appreciate your support. And kind of what we're looking for today for everyone is to share some information with you, share a tool with you, get some feedback and ideas from you, and also suggestions of how this tool could be made even more useful for your business, any upgrades that you might want to make to it. So Kate Angel on our team is going to facilitate today's discussion with Anthony and Marty Peckles from Bayer MaterialScience, who's going to demo the tool. There are a couple of ways for you to participate. I'm going to help on the back end with that. But if you have any questions or comments during the discussion, feel free to type it into that little enter a question for staff field on your control panel for GoToWebinar. And you also have the opportunity, if you would like to raise your hand, and once we get to a good break point or one of the built-in points for questions and answers, we will open the floor to both facilitate answers to what you've submitted online, and if you want to raise your hand, we can make you live as well and take your questions and comments and feedback that way. So I'm going to turn the floor over to Anthony.
Well, it is afternoon, so good afternoon, everyone. I'm happy to talk about this topic of condensation and just really wall performance. I've been focused on enclosures for probably most of my career here at IBACOS. But I wanted to start off, and I'm sure everyone knows that trends in the industry are, energy efficiency, building a tighter home, with all that said, trying to understand the interior environment and how wall performance actually is critical to have a very good, durable wall and a home as a whole. But I did some research when Betsy asked me to do this. I said, let me look at the past 100 years. And we had an actual, this American Builder magazine in our library. And I found it, and it's from May 1924. And this was the first mention of insulation in a wall assembly. And it was actually JM that actually had this advertisement. And they were advertising almost exterior insulated sheething. It wasn't a board product. It was sort of looking at higher performing felts. And it was actually made by an asbestos material, which obviously has been banned in the industry. But the intention was going in the right direction. Obviously, we sort of fell away from that over the last 80, 90 years, but I would say over the last 10, 15 years, we're sort of coming back to it. Trying to put insulation on the exterior side of wall assemblies is, in my mind, the best way to control condensation. So I just wanted to start off the presentation by showing this article. Next slide. So condensation, I just want to make everyone aware of what the definition of condensation. Obviously, it's when an air mass gets, sort of increases its pressure, its vapor pressure, and it needs to find a point where it could sort of distribute its vapor to a lower pressure environment and create condensation because it can't hold any more moisture. And I put this picture up on here because this is sort of the first evidence that we see as homeowners as condensation occurring on walls. It's actually occurring most of the time. We see it very visibly on window frames. And obviously, this is a window frame that's aluminum. And obviously, the reason why it's condensing, and obviously because the temperature of that window frame is below the dew point temperature of the interior environment. And we've seen, and the reason why I put this up is we've seen the window industry change some of the performance criteria to having a condensation resistance index. So I'm wondering, should manufacturers of insulation materials create a condensation index for their own insulation materials in wall assemblies. That may be a stretch, but it's something that we should all be thinking about. So the focus of this presentation, try to understand the facts of condensation. So I think if we keep temperature of these building materials above a dew point, condensation will not occur. Obviously, the dew point temperature in the interior environment is very dependent on the environment that the occupants create in the home. If the occupants live in the home, and they're in the home throughout most of the day, they cook a lot. If the home is fairly new and there's building materials that are still drying out, well, the dew point in that home environment will be a lot higher, which means that the building material temperatures have to be a lot higher also. So that's a main fact that I sort of want to focus on. But the other fact is cold materials, when they do get wet, they stay wet for a long period of time. And so an example I always like to use when I talk to builders is if you look at your driveway in the wintertime and you have a pool of water, a puddle, it takes a lot longer for that puddle to dry out because it's cold outside and the surface temperature of that driveway is cold. If you have that same amount of water and puddle in the summertime, it dries out fairly quickly. So sort of the same sort of concept. And I'm trying to keep this as simple as possible. And that's our whole goal of this presentation here. Third fact is when you have air movement in wall assemblies, air tends to bring a lot of water vapor into that wall assembly through diffusion or through holes. And fourth, when water vapor moves across assemblies or through environments, it's not really dependent on temperature, it's really dependent on concentration. So a mass of air that has higher concentration, that mass of air that has high vapor is going to want to move to a lower concentration of air or surface. So those are the 4 key points that I want to make as facts in regards to condensation in wall assemblies. But just to talk about diffusion, obviously I would say 99% of our walls are sheathed with gypsum wallboard. And gypsum wallboard is not a vapor barrier. It allows vapor to diffuse through the product. And you can see here, you know, a third quart of water passes through a 4x8 sheet. This is fairly well known in the building science arena, but I'm just trying to let you know that water vapor does pass through building materials. Now, if we have a 6 mil polyethylene sheet, it's considered a vapor barrier, so we will not see a lot of vapor pass through those types of materials. But in a drywall sheathed wall, if there is a hole, and there are many holes like electrical outlets or plumbing penetrations, that hole and air leakage will bring a lot more water into that wall cavity. And in those cavities, let's say, it's more prone for condensation to occur in those cavities because now that water that's passing through that vapor that's passing through that hole is looking for a really cold surface to condense on. If it doesn't see a cold surface to condense on, it's not going to condense, basically. So let's focus on temperature. Temperature, I think, is what architects, engineers, builders, building science need to strive to understand. I think that simple concept will ensure that building assemblies will be more durable. I think what I've seen through the works of building scientists and others in the industry trying to help builders or architects and engineers understand performance of wall assemblies, we're starting to add other characteristics to, like vapor diffusion through wall assemblies and looking at different building materials, looking at hydrothermal analysis models, and all that is great, but I think we need to try to understand temperature. I think if we look at some old building science books out there in the 50s and 60s, they really focused on temperature as trying to control the interior cavity environment. So I drew these 2 wall assemblies because these are some, I guess, the most dramatic 2 wall assemblies. One where we have all the insulation outboard from the cavity or frame of the wall, and the other is having all the insulation in the cavity. And the key here is when we have insulation that's outboard of the frame, we can create a dew point in the wall cavity that is above the dew point of the interior environment. And obviously, by putting insulation outside the frame, we can keep that whole frame structure a lot warmer. That's the main point I wanted to make here. When you have insulation that's within the cavity, now we have thermal bridging occurring, but we also have interior cavity temperatures that are higher than the dew point temperature in the home, which means if vapor or air leakage occurs behind the drywall, there are surface temperatures for condensation to occur. So keeping surfaces warm in the cavity is the key here. So lastly, I think if I look at over the last 70, 80 years, I know Owens Corning brought in their fiberglass bat in 1938, which is a vapor permeable product, which is a very good insulator. I think some of the downfalls with vapor permeable insulation, it creates a little bit more potential and risk when we talk about condensation in higher performing wall assemblies. So vapor permeable insulation allows air leakage to occur if there's no vapor barrier or air or vapor retarder behind the drywall, and allows for potentially cooling off condensing planes. So if we look at a traditional cavity insulation wall, the condensing plane is typically behind the OSB or behind that exterior sheathing. If we look at the right side graphic here, which is a vapor impermeable insulation, whether it be a rigid board or a spray foam product, the condensing surface is really the interior surface of the spray foam or rigid board product in the cavity, or if it's the outboard. So, and typically, those surfaces, those condensing planes, will be warmer. Now, depending on the climate, you have to understand how thick do I need that board or insulation to be to warm up those interior surfaces. So that's the main point. And then understanding, obviously, when you have a vapor impermeable insulation, whether it's left or right or inside or outside of that board product, you're going to have drying occurring and vapor drive occurring within its own environment. So when we have a vapor impermeable insulation, whether it's outboard from the cavity, we're allowing that cavity to just dry inside the home, and any vapor that gets absorbed or any water absorption that's absorbed in the cladding system, we're allowing that cladding system to just dry up on the outside. So it's that vapor impermeable insulation is almost creating multiple control layers. So it's a vapor control layer, it's predominantly an insulation thermal control layer, and it could be an air control layer. So it brings a lot of benefits and a lot of sort of headaches out of builders or architects and engineers to understand, because it is a complex wall assembly, and doing it right the first time makes a lot more sense. So I just wanted to go through some scenarios that, some pictures and projects that I've worked on over the last 15 years and show you some typical examples of what I've seen in the field. These examples are new homes that have been built. These are examples of basement scenarios. And obviously, condensation is more predominant in heating dominant climates, so climate zones 4, 5, 6, 7. So this is one where obviously it's a concrete foundation wall, and obviously we're seeing a lot of condensation, and in those corners we're actually seeing frost because it was so cold. This foundation was actually insulated outside, but it was only below grade. So the above exposed area, about 14, 15 inches, was exposed, and it caused condensation to occur. Now, why did it occur? Well, the main reason why that interior surface in those corners, the temperature was below the dew point temperature in the home. So the other aspect I want to talk about, in new construction, especially when we build basements, we do introduce a lot of moisture during probably the first 18 months of the home's life. Because concrete has a lot of water in it, it raises the interior relative humidity inside the basement and ultimately inside the whole house. The other areas that we see a lot of is when we see insulation applied to band joist areas, where typically they're insulated, but we're allowing the moisture-laden air to basically get in contact with a cold surface. And in this case, you'll see the bottom left, we're seeing an OSB band area. That actual band area was an insulated band area, but it was actually covered. You'll see fiberglass bats that were stuffed between these open web joists. And what happened was, it was meeting the R value of that climate zone, but what happened was the fiberglass bat that was stuffed in there actually cooled off that OSB insulated band surface to lower to the dew point temperature. And the issue we saw here was, well, fiberglass is not an impermeable insulation. It was a vapor permeable insulation, so it was still allowing vapor to diffuse through the bat and condense on that cold surface. And then on the top left is something very similar. The builder insulated the between floor system with a rigid board product. And the same scenario here, he put an extra layer of bat insulation over top of it, but it was still condensing on the foam board layer because that bat was cooling that surface off, but still allowing moisture to diffuse through it and condense on it. Obviously, there's no drywall in these scenarios. If we had drywall, it would sort of limit the amount of vapor to pass through to hit that assembly. But I just want to show you the most apparent areas that we see condensation occurring. And then the bottom right and top right is when we have sort of these lookout basement walls, or we call them garden walls, where there's a walkout basement and there's a sort of a framing portion of it, where typically these framed walls are insulated with fiberglass blankets. And these are areas where the blanket has a vapor retarder on it, but they're not sealed very well. And these little gaps cause vapor to pass through leakage points and condense on cold sheathing surfaces. And then, so what about spray foam or other rigid board products? So these are, best practices that we see. When we have impermeable installations, we can address a lot of these surface temperature areas, and we can increase these surface temperature points by installing vapor impermeable insulation in these areas. Now, these are all installed inside the home. They can be installed outside the home also. So I'm just showing you one scenario where insulation that's impermeable can be applied on the interior side, but also can be applied on the exterior side. And predominantly, in exterior applied insulation is the best practice out there right now. So what motivated IBACOS to create this tool that Marty's going to go into in a few seconds? Well, we've worked with WFI. We have WFI experts in-house at IBACOS. So I'm not saying that WFI is a very poor tool. I'm saying WFI is a very complex tool. And what we've seen over the last probably 2 or 3 years, we're seeing a lot more architects, engineers, HERS raters starting to be trained in WFI. And what we've noticed is when we get requests to review a WFI model, we see variation in differences across the board. And a wall assembly that, from the IBACOS perspective, looks not very good because we have a lot of experience. We're seeing that these models are coming out really good. And we're trying to understand why. And I think we can't come down to the root cause of this. Is WFI, it requires materials that have specific properties. And you have to define those specific properties in WFI. And WFI has a standard default library database. But I know for a fact, every time I try to run a WFI model for a specific wall assembly and for specific material that a manufacturer makes, it's very difficult to get all these different properties. And I just listed probably 1/3 of the properties that WFI needs to know to do a proper model. And I know that there's a lot of people using WFI that are not getting the right properties. So the reason why we created this tool is just to create a very simple tool that looks at temperature and tries to give a quick understanding of how well is this wall system going to perform in the built environment. So that is what I wanted to say today, and I think Marty's going to show some examples on how he uses the tool and how effective it has been with some of his clients that he works with.
Okay, Marty, you should have control, and go ahead and take her away.
Good morning,
Oh,
everyone.
I'm sorry. I'm sorry. We have Kate stopped me. We have time for one or two initial questions. Doesn't look like we have anything typed in at this point from anyone, so we probably will keep going, and I don't see any hands raised right now. But again, you can raise your hand or type in a question through the chat function. We'll have another Q&A, formal Q&A break after Marty goes through the tool as well. And be thinking about what wall systems you guys build. He's going to give some scenarios with the tool in a few minutes. But as a builder in the Alliance, you have the opportunity, if you look at this tool and think, hey, how would this work for a wall system that I'm currently building? We're going to send the PDF of the slides out after the meeting, and you can go ahead and look at the types of information you need to provide for the tool. And if you're interested, you can send the specs for your wall system to me, and I'll coordinate with the guys to follow up with you to let you know how that wall system performs in this tool as well, and get that information to you also. So now I will hand things over to Marty.
Good morning and good afternoon, depending on whatever part of the country you're in. So we're gonna talk about this condensation calculator we developed, and we're gonna use a particular builder named Shady But Lucky Builders, and we're building at Grisolia Manor Estates. So we'll jump right into it, and if I have control, you guys got to give me control.
Okay, perhaps it uncontrolled you. Your checked as having control. I'm going to recheck you. Try now. Is it working for you?
Not yet.
Okay, just give me a holler. I will just say next, and I'll advance them for you. Technology is fun, isn't it?
Sounds good to me. Next.
Okay. All right.
So to have this calculator actually work for you, we have to put quite a few inputs in, all the way from the cladding all the way to the drywall. So we've color-coded the drop-down selections for ease of viewing this slide. We'll start with the cladding on the outside. In this particular case, we've selected siding, aluminum vinyl with a hollow back, but you can also enter brick or stone veneer, stucco, wood siding, hardy board, or beveled lap. Also an aluminum vinyl with half-inch insulation, or T111 of half-inch or 3/4. And then we identify the exterior rigid insulation as either EPS, polyiso, XPS, or sprayed closed-cell foam, or identifying no rigid insulation at all. And when we do identify these board stocks or spray applied, we also enter the thickness value that we're installing. And we identify the sheathing, the OSB, either half-inch or 3/4, or thermoply, or no rigid sheathing at all. Then we identify the framing member, the cavity depth of a 2x4, 2x6, or a 2x8. And then we identify whether or not we're going to have any spray foam, whether or not we have open cell or closed cell, or none at all. The cavity insulation, we've, in this particular case, selected an R19 batt. You can also choose cellulose, a dried blown-in fiberglass, or a wet blown-in fiberglass, or different batt values, R11, 13, 15, 19, 21, and 25, or no cavity insulation whatsoever. And then again, drywall or an interior rigid foam, EPS, polyiso, or XPS. Next. So what we've identified is 3 different cities with 3 different climate zones. To give you an example of how this tool works and the different wall assemblies that we're going to run a comparison to and see how the indoor relative humidity presents either a risk or no risk at all. Next.
Okay, we do have one quick question here asking whether this tool is based on the HAM analysis approach.
Based on the ASHRAE dew point analysis approach.
Okay. Take her away, Marty.
Next. So Minnesota, they have an adopted modified 2009 code. Here you can see in a wall frame we have 19 required R value or 13 plus 5 exterior. Next. So as we showed for the entries, in this particular case, you can see we've selected Minnesota as our location. It's identified as a Zone 6A. You can see this on the bottom left of the slide. It automatically identifies the average winter temperature of 16.7. An indoor room temperature, we're going to model at 70. And an interior room relative humidity of 30% is the average. So in this particular case, we've modeled the wall, and we're going to do the same wall scenarios throughout all 3 cities for ease of understanding. We have vinyl, no hollow back, no rigid insulation, half-inch OSB, and a 2x6 wall. And it will vary, 2x6 or 2x4, depending on how big of a wall we need to achieve our required prescriptive R value. In this particular case, this model shows no spray foam. We have a fiberglass R21 bat and half-inch drywall. So knowing that our average indoor room relative humidity is 30%, you can see we have a marker, black triangle with a line. It identifies that is our average indoor relative indoor humidity, and we are in a risk. Basically, it's saying that we will have a condensation potential at any time when the indoor relative humidity is above 13%. And that you can see on the bottom right underneath the other red box where it says inadequate maximum acceptable indoor relative humidity of 13%. So now we ask ourselves, what can we do next? So one scenario would be to apply exterior board stock. And in this particular case, we've chosen to install 1 inch of polyiso. So you can see now, all of a sudden, our average 30% relative indoor humidity is still at risk, and we still have a condensation potential, but we've reduced that risk and brought our maximum acceptable indoor relative humidity to 28.9. We're almost good, but we're not quite there yet. Next. So now we take another scenario, a hybrid approach. We can apply 1 inch of spray foam and then supplement the remaining R value with an R13 bat. Now you can see that the 30% average indoor relative humidity is in an acceptable zone. But we all know that based on indoor environment, mechanical systems, ventilation, occupancy behavior, whether or not it's a new home or an older home, your relative humidity will vary, and it'll change throughout the year. And your systems will, ventilation strategy, mechanical systems, all are dependent on what that indoor relative humidity is. What we're just saying is based on the data we have, the average, you're in an acceptable zone. Next. So our next wall assembly, we chose to install in a 2x6 wall with 5.5 inches of open cell to achieve our R value of R19 requirement. In this case, you get an R20. But now all of a sudden you can see the acceptable zone is all the way up to 98% indoor relative humidity. You have no condensation potential throughout the entire range of moisture that could possibly be in the air. Next. So now we choose to go to Colorado. We have an Energy Code 2009 IECC. In this case, we have a requirement of 20 or 13 plus 5. Next. So as before, we're going to start out with the same wall assemblies in the same scenario. In this case, we need to get an R20, so we install an R21 bat. And in this particular case, our average indoor relative humidity is 35%, with an average winter temperature of 31.7. And in this model, our maximum acceptable indoor relative humidity is 24%. Next. As before, we'll run a scenario with board stock on the outside, again, 1 inch of polyiso. And we've now reduced the framing to a 2x4 and installed an R13 bat. No sense in maintaining a 2x6 wall if no need to, and we can still achieve the R value by prescriptive measures. So in this case, we have a maximum acceptable indoor relative humidity of 42%. But again, is it always going to be 35% indoor relative humidity? We don't know. Next. We run the same hybrid scenario here, 1 inch of spray foam and an R13 bat. And we now increase that relative acceptable indoor relative humidity to 48%. We've actually achieved now, we're 13% higher than the average, so not too bad. Next.
Marty, there was a quick question here that says, but filling a 2x6 wall cavity with open cell foam in Minnesota does present condensation risk. Oh, I'm sorry, this is a comment. Because of the, it says OCPFF. Am I reading that?
Open cell spray polyurethane foam.
Thank you. It is not vapor impermeable.
That
so
is
any
correct.
feedback on that, guys?
Sure, and you know, so we know that different open cell foams have different perm ratings. In this particular case, our product, I believe, off the top of my head, is a perm, 21-inch perm. So dividing that by 5.5, you're going to end up at. Oh, I guess I got to get my calculator out here, huh?
Yeah, and in some of those cases in climate zone where Minnesota, there may be extra, different paints that we're putting on drywall to decrease the permeability of that wall assembly. But again, the key question here is warming up that interior condensing plane.
Sure, and then back to the perm. So at 5.5 inches, you have a perm of 3.8, not quite a class 2 vapor retarder. So as Anthony said, then you would consider putting a vapor retarder coating either directly over the insulation before drywall, or you could apply a vapor retarder coating over the drywall to prevent any vapor diffusion. And as we already have identified that primarily we need to focus on air and then vapor as well, definitely not something to disregard. But when we have large delta T's between the indoor and outdoor temperatures, and we have relative humidities that can create a vapor diffusion scenario, absolutely need to consider putting a vapor retarder coating on the drywall or the foam itself.
Okay. There's one more question. There's actually two in here, but we're going to hold on to one of them for now. What is the assumed air infiltration for the software?
There's no assumption on air infiltration, so it's all a conductive model of looking at temperature across the wall assembly profile.
Okay. Take her away.
Well, actually, I didn't even talk about the other slide. Want to just back up real quick?
Sure. There you go.
So again, as before, with just a model of condensation potential, here all of a sudden you have a safer scenario. You're not in risk. Next. So we have Houston, not a cold climate. We're focusing more on a cold climate scenario on a condensation potential, just to give you examples and more climate zone scenarios. We chose Houston, a popular area where people are building. And in this case, we have adopted Climate Zone 2 with a wood frame wall of an R13. Next. So in this, again, first wall assembly that we have modeled, we have an R13 bat. We have an average indoor relative humidity of 40% and a maximum acceptable indoor relative humidity of 55%. As before, we already discussed that, that relative humidity will vary. Will not always be at 40. At sometimes it can be as high as 60, 65, or even higher, depending on what part of that building we're in. If you're in a bathroom and it's not being ventilated properly, we could possibly put that wall at risk. Next. So here again, we have an exterior board stock design, and we have an R11 in the wall, and we've raised the maximum acceptable indoor relative humidity to 70. So now we're creating a safer wall. Next. The hybrid approach, another scenario with 1 inch of closed cell and R11 bat, and we've raised the maximum acceptable indoor relative humidity to 74%. Next, at an open cell scenario and a 2x4 wall, reaching the R13 required value, we've now raised the acceptable indoor relative humidity to 99%. Next. It's up to you guys.
All right, Marty.
It's yours, Anthony.
Yep. Thanks for that analysis. I think that was great, looking at the different scenarios and how different insulation materials can improve and enhance the durability of condensing planes, really, and condensation occurrences in different climate zones. But our next steps, this tool we created about, 5 years ago, but over the past 2-3 years, we haven't done a whole lot to it. But we're at a point now where we think we can expand the comprehensiveness of the results that it spits out. We're looking at potential, doing a version 2, but obviously we need some support from the industry to do that. Bayer right now has been licensing the tool, but there are some things we want to address. Right now, it's really a conductive dew point analysis tool, but we're thinking of adding some features to it, looking at almost an hourly analysis of condensation occurrences across a wall assembly. So give it a little bit more features, but don't want to make it as complex as other modeling tools in the industry today. And we're looking for feedback from you guys and gals on what would you like the tool to do when talking about wall assemblies and condensation occurrence.
Okay. Well, we do have a few questions here. The first, which you sort of answered, but if you could clarify, someone was asking if the tool is available on the web for public use.
The tool is currently not available on the web for public use.
So at this point, if anyone wants it, from my understanding, if anyone wants to use it, because Bayer's licensing it, anyone could approach Bayer and be able to get that information. And since we created it, they could approach us and be able to get initial information as well.
Correct.
And obviously, from a usability standpoint, I would imagine we would love to take this public. We just need more capacity to do that. We need more support to do that.
We need more support, more funding to do all the upgrades that we want to do.
Right, and I would imagine as well some feedback from you guys, and we've got a couple other questions here that might start to address that, on upgrades that you would want to see to it, what would make it useful for you. One of the other questions here is, so all of these examples that you provided dealt with condensation issues on interior walls during the winter. Is that correct?
That's correct.
Okay. And then the other last statement here, and then I have a question or two of my own, is to determine condensation potential, the model must make an assumption related to air exfiltration. Example, the condensation plane is assumed to be exposed directly to indoor air while it is cold due to its location within the thermal control layers, right? That was
Repeat the question, sorry.
Let me open the question so you can see it, because there's a lot of words for me to repeat for you, Anthony. Take a look at this directly here on your screen, and then that will be a little bit easier for you to comment on. Okay, it's right here, this one in the middle, right, or right there if you look at it, right there on the screen. And then my other question for you, as you're reading that and trying to absorb it and respond to it, is, so if you can just touch on the dehumidification part that we could do a follow-up webinar.
So in regards to the air infiltration is a huge component to understanding condensation. The calculations on the ASHRAE dew point do not take into account an air leakage movement across the wall zone. It's a conductive calculation that looks at resistance of materials and how it raises temperature of materials. Now, if a home has a lot of air exfiltration, yes, you'll have more potential for condensation to occur in that cavity because you're just moving a lot more air through that wall assembly. So hopefully I answered that. Now, could the next version look into air infiltration or exfiltration across? It could, but again, I'm trying to create a simple model here where if we just look at temperature and we raise the temperature enough where we could have a little bit of leakage and still be okay. You know, that's the key here. And then the other question, Betsy, is?
Oh, no, that was actually the last question. My question to you, Anthony, was just for people who may have observed and seen that there was a tab there that said dehumidification. That was a whole other area in the tool that we didn't go into today that we could show in a subsequent call. Can you just give a 30,000-foot snapshot, you know, without going into an exorbitant amount of detail about what that is?
Yeah, we could talk on length in regards to dehumidification. But the tool has another aspect to this where we're looking at, in a higher performing home that is airtight, what happens in the interior environment in regards to dehumidification. So to think of the dehumidification side of this tool looks at hot, humid climate zones, and how do those higher performing homes address dehumidification of air. So it looks at the inputs are, to just give you a brief overview, it looks at the volume of the house, amount of infiltration calculated by a blower door test. It looks at the capacity of the equipment, the actual loads of the home in regards to heating and cooling load, and it asks for ventilation rate in regards to 62.2. And it gives you an assumption of the impact of the humidity in the home and what is the need for that city, let's say, of dehumidification. So it looks at almost, you know, trying to prevent, let's call it the bad word, mold in homes. How do we control the interior environment so we don't create issues of mold? So that is another aspect of the tool that we'll probably talk about in the future, but for now we just want to talk about condensation because it's a big topic on its own.
Just want to make people aware of that once we send out a PDF of the slides so you don't say, hey, what is that whole other tab there that you guys didn't touch on?
Yeah, I have a question for Marty. Marty, obviously you've used this tool as Bayer. Who do you interact with regarding the tool in the industry?
I would say that the most frequent call I get is from insulation contractors that are designing a wall insulation system in an area such as where I live here in Utah or in Colorado and you know, sometimes in Minnesota or so on, where the plans examiner knowing that there's always been confusion and as to what an adequate hybrid system will serve well and have a lower condensation potential, and whether or not it's a safe wall, they'll call me, or in some cases I have quite a few code officials in the state of Colorado and Utah that I've worked with in the past will call and just verify, hey, I've got a guy submitting this type of wall assembly, are we good? And we'll go through the entire model, and as Anthony touched briefly, the dehumidification tool goes into a lot more further extent as to determine how many days throughout the year and what months you're going to be exceeding the average relative humidity, and for how many days and what the increased relative humidity is by 15, 20, 25. It actually breaks it down quite detailed. And actually with that, in the condensation tool, you'll be able to evaluate whether or not at some point in time during the year you'll have some risk. I also have architects that I'll work with on a commercial level to some degree. I've had people run Woofy. Unfortunately, it wasn't the paid version. It was an unpaid, free version on the web, and an architect paid another architect to run it, and then saw this little blue line with a kind of moisture potential in the wall, and we had 3 inches of closed cell foam in the wall, and they wanted to put a poly viscreen over the closed cell and then put the drywall on it. And they thought that I was trying to sell them something, but I actually tried to keep them from having a potential problem, and I showed them the tool, and they understood that the viscreen was unnecessary and actually would pose a potential problem. So working with architects, contractors, plans examiners, and some builders I've shown this to, they see some value in it. And it reduces their liability knowing they're building a safer wall.
Okay. There are 2 other questions, one of which Anthony was just telling me will require some more specific information on the asker's part. So we're going to follow up with you offline to get a little bit more detail and answer that question. For those of you who are on the line who didn't ask the question, when we do the follow-up information, we'll provide the question and the answer to everyone so you can see what was asked. But we don't want to get into that at the moment without more detail to give a false answer. But one of the other questions that's up here that I can answer is, can we please share the link for the recording of the webinar so that I can share it with others in my company once we have that in place? Absolutely. Basically, the web page that connects to this meeting will have both the PDF of the slides from today's discussion as well as a link to the recording of the webinar, and we will make that available to everybody on today's call. It will also be in the next issue of the newsletter. So if anyone else on your team is getting the newsletter, they can find that information there as well. We don't have any other specific questions here at the moment, but if you have a last question or 2 and you want to pose it, feel free to type things in. I have a couple of orders of business that I would just like to share with people before, or is there another thing on here, Anthony?
Well, I just wanted to mention one thing. Obviously Marty and I have a great relationship, and we talk about this tool a lot. And I think some of the things that we've been talking about, looking at the advancements of the tools, almost looking at it as, can this tool look at block walls so we can address some of the Florida markets? Can it look at steel studs? And is there an opportunity for this tool to look at roof systems?
Mm-hmm.
There is. Obviously, it's just a lot of work to start adding all these wall assemblies and materials and the analyses part. So, but that's what we're thinking of trying to do.
But it would help to get feedback from
Absolutely.
alliance builders and sponsors as to what would you actually use and what kind of information might you be able to provide or support might you be able to provide to add more functionality to the tool as well.
Yep.
So I'll check in another moment to see if there are any other questions since we just kind of dove in there. But before we close today, I wanted to make sure that I Remind you that the information was sent out for the Alliance annual meeting. It's the 12th and 13th in Charleston, South Carolina. We have a great program planned. There's a nice casual networking event for people who arrive early on the 11th, all-day sessions on the 12th, and then the sessions will continue on the 13th and wrap up by 3 in the afternoon. KB Home and Shea Homes are keynoting. We also have some folks from Newtown Builders and fingers crossed a couple other builders I'm in the process of closing as presenters as well as a finance panel. And all of those experts down at the bottom of your screen on the left are focused on resiliency in housing from the Insurance Institute for Building and Home Safety, Flash, and Simpson-Strong-Tie. That, I think, is going to be a huge issue as we move forward in the future of home building, as well as what's going to happen with water in addition to energy efficiency. So would love to get you guys engaged in the meeting, and look for your email if you haven't seen it already. If you have any questions, feel free to give me a call or forward those to me by email as well. And we'll continue to send you updates as they become available. And the early bird registration for the annual meeting, which is a discounted rate both for the hotel room and the registration itself, ends the 12th of October. So take a look, see if it's of interest to you, and hope that you're able to participate. Kate, are there any other questions over there in the queue that are new?
Nope, I think we have answered all the questions that we can.
All right, then in closing, I would just love to thank Marty from Bayer MaterialScience, both for Bayer's support in creating the initial development of this tool along with IBACOS, and certainly for joining us today and presenting the tool. And thanks to Anthony for stepping in at the last minute and being a good little building science expert for us.
No problem.
And thanks everyone for participating. Look for follow-up materials by email, and have a great rest of your day.